Okay, boys, here are some videos. I picked 3 problems out of chapter 19 to do for you. I was getting to feel kind of bad because I hadn't heard from you, you didn't write, you didn't call, and then I cleaned out my junk email. And for some reason, I found several emails in there from Boston, so sorry about not getting back to you on those. But anyway, here is the videos. I picked out problem number 2 because this is an F test. And problem number 4, because that's a 2-sample t-test, and number 5, because that's a confidence interval when you have 2 samples. Now the F-test is done to determine if the variances are equal or not. Many times that's going to help us determine if we need to pool the variances for the standard error of the mean, or whether we don't have to. So it's generally a really pretty easy test to run. To do an F-test, you have the 2 sample variances, S sub 1 squared and S sub 2 squared, and you're going to divide them, and you're just going to put the larger one on top, the smaller one on bottom. And then you'll get a decimal because you're putting the larger on top. It's going to be greater than 1. And then you have sample sizes, and you need to make sure you keep which sample size goes with which. And we're going to look up in the table in a minute the critical value. But remember, degrees of freedom is just n minus 1. So the degrees of freedom for the first sample is going to be 3, and the degrees of freedom for the second sample is going to be 5. So the degrees of freedom of the numerator is n sub 1, so that's 3, and the degrees of the denominator is 5. Okay, to do this we need to go to our table D, and I don't think it's in that packet of information, but it is at the back of your book. And the top of table D, I don't think they put in that packet because it's long. It's 4 pages, but this is what table D looks like. And in table D, we're finding the probability. P is the probability of the area in this right tail. And the way you read this table, you're going to locate the degrees of freedom of the numerator. And that's why I said it was important to keep S1 separate from S2. So the degrees of freedom of our numerator was 3. So we go to the 3 column, and the degrees of freedom of our denominator was 5. So we're going to go down here, 5 in the left column. And where these 2 columns intersect, we're going to be using one of these values. And if I want a critical value at the 0.10 level, I would use 3.62. At the 0.05 level, I would use 5.41. And this test, they're asking us for the critical level for the 0.05. So we're going to use 5.41. Now I noticed that in their answer, they have more decimals because they're probably using some other kind of statistical software. If you enter 5.41, it'll count it correct. So don't worry about that you're off minor decimals because it depends on how many places you take your decimals out to when you do your calculations and what tables or software you use. But that's how you use that table there. Let me just pull this down here for a minute. In B it says, in a test of equality of standard deviations against a 2-sided alternative, this statistic has the value of F equals 2.18. Is this value significant at the 10% level? So in that same column, we're in column 3, row 5, but we're using the 10%. So 3.62 is going to be our critical value. In order for us to reject the null hypothesis, our test statistic, our test F, has to be greater than 3.62 in order for us to reject the null hypothesis. So 3.62, 2.18 is not greater than our critical value, so that means this value doesn't fall in the tail, which is the rejection region. So we do not reject at the 10% level. Then it wants to know if it is significant at the 5% level. Well, remember, as alpha gets smaller, it becomes harder to reject. So if we didn't reject at 10%, we're not going to reject at 5%. If you'll remember, in the 3rd column, 5th row at the 5%, it had to be greater than 5.41. And since it wasn't greater than the 3.62, it's not greater than the 5.41. So we would not reject at that level either. So that's just a little bit about the F-test. I think there might be one other question in there that you can practice. Yep, it's number 3. Okay, number 4, we're going to talk about a 2-sample t-test. And we would use this test whenever you have 2 samples that are taken from 2 different populations. This is how this differs from what we did in chapter 18, where we had 2 samples, but we would find the difference in those. The samples were 2 samples from the same or very similar populations. So I'm going to show you a little bit from your notes. If I can get my camera to come back up here. There we go. And I'm on the second page at the very bottom of the first column. There's the basics of inference we did in chapter 18, inference about means. Here's the 2 sample stuff that we're going to get to here. We're going to do a confidence interval next. What we're going to do is the t-test for this one. So a 2-sample t-test, it's at the top of the right-hand column on the second page of your notes. And the null hypothesis, as in all the other tests, is that there is no difference between the 2 populations. So mu1 equals mu2. Sometimes you'll see this written as mu1 minus mu2 equals 0. If there's no difference, that means the difference between them is 0. So these are independent, simple random samples from normal populations. And when it says with conservative p-values, we're going to be using a table. Your PowerPoint showed you a lot more complex formula for degrees of freedom. We just take a simple one that's a little bit more conservative, meaning it makes it just a little bit harder to reject. So if we do reject, we know that there's definitely a difference. Okay, so to find our t-score, we're going to be subtracting the means of the samples. We're going to be dividing it by the square root, and all of this is under the square root. S sub 1 squared, which is the standard deviation of the first sample squared, which is the variance of the first sample, divided by its n, the size of that sample, plus the variance of the second sample, divided by the n of that sample, n sub 2. And for degrees of freedom, we're going to be using whichever one's smaller, n1 minus 1 or n2 minus 1. And if the degrees of freedom row isn't in your table, make sure you're using always a smaller degrees of freedom, never round up, because then that's less conservative. Okay. So in this problem, we're given that we have 2 groups. Men, we have 562 men, and their average is 1.90. Their standard deviation is 2.75. For the women, there were 762 women, and their average was 0.96 with a standard deviation of 1.94. We suspect that men are more prone to road rage than women. Carry out a test of that hypothesis at alpha equals 0.05. State the hypotheses, find the test statistic and the p-value, and state your conclusion. So remember, the null hypothesis is always going to be the equals case. So we would fill that in with equals, which it looks like you guys did. And this just means the mean of the men, that's what the sub m is, and mean of the women. The alternative hypothesis, here's where you have to really think. Do they think men's road rage is greater than women's, is less than women's, or is just not equal to women's? And in this case, it said yes, they're more prone to road rage than women. So the mean of the men is greater than the mean of the women. Okay, we got a 6.93 for our test statistics, so we're going to talk about how we get that. I'm going to bring up some paper I can write on here. Come on, paper. There we go. All right, there's the top. All right, T is going to equal the difference in the x bar, so 1.90 minus 0.96 divided by the square root of the standard deviation of the first group squared divided by how many were in that group, so the n that went with the men there, 562, plus s squared for the women, so 1.94 squared, divided by the number of women in our sample, 762. So you're going to put this in your calculator, and as you calculate this, be kind of careful. Go ahead and subtract this, but press enter to force it to subtract. And then put divided by your calculator, and I can't remember you guys' 84 pluses if they have the newer update where when you press the square root you can see exactly what's under it. You don't really need any parentheses other than the parenthesis at the very beginning, at the very end, if it automatically opens one up. But you're just going to put in 2.75 squared divided by 562 plus 1.94 squared divided by 762. No special thing there. And I think when you enter all that in your calculator, you come up with 6.93. Or at least I did when I put that in mine. Alright, so that's where the test statistic over here, 6.93, came from. The p-value, now this is kind of a funny p-value, and that's again because they're using some software rather than the table. So we're going to go to Table C, which we use whenever our test statistic is a t-score. The degrees of freedom here, for the men's group, the degrees of freedom would be 561. For the women, it would be 761. And to be conservative, you use the smaller of those two. So our degrees of freedom that we're going to be using is 561. Now, most tables, if it's a table, don't have those. If you use software, it'll calculate that. So in our test C, just show you what the top looks like here. The degrees of freedom are in that left column. And you're going to see in this column we don't have a 561. 561 is going to fall somewhere between 100 and 1,000. And in the problem, I think it tells us to use, I'm not sure if it's this one or another one, but we would use the 100, use the one that is smaller than the degrees of freedom given. So in this particular problem here, we're in row 100, and we need to look up 6.93. We start at this side, and all of these numbers are less than 6.93. In fact, when we get clear to the end, they are all under 6.93. 6.93 is going to be out here somewhere. Well, our p-values are in these two bottom lines. We have a one-sided test because it's the mean of the men is greater than the mean of the women instead of just not equal to. So the one-sided p, notice those p-values are getting smaller. And since we're off the table over here, we know that the p-value is going to be less than 0.0005. Now, when you enter this in the answer blank, I would just put it in like this. Go ahead and just use your less than. When it grades it, it'll probably tell you that that can't be understood or whatever. When I grade the test, I will understand exactly what you mean. You could even type in p, or p-val is less than 0.0005. That's a very small p, and remember small p's mean we reject. Since we have our p is smaller than the alpha of 0.05, that means there is evidence that men are more prone to road rage than women. The subjects were chosen by random digit dialing of telephone numbers, so that is randomly done. Are the conditions for the two sample T inference satisfied? Yes, because the sample is a random sample, and it is, and this one has really large sample sizes, so it makes the normality condition unnecessary. So that's just how we would run a t-test. It's very much like what we did last chapter, but we're using that new standard error of the mean, the square root of s sub 1 squared over n1 plus s sub 2 squared over n2 instead of just using s divided by the square root of n. So a little bit more complicated. All right, next we're going to go to number 4, And in this one, it says the air in poultry processing plants often contains fungus spores. Inadequate ventilation can affect the health of the workers. The problem is most serious during the summer and least serious during the winter. To measure the presence of spores, air samples are pumped to an agar plate and colony-forming units are counted after an incubation period. Here are data from the kill room of a plant that processes 37,000 turkeys per day, taken on 4 separate days in the summer and in the winter. The units are CFUs per cubic meter of air. So we have the summer, and we have 4 data points for the summer and 4 data points for the winter. Those are 2 separate populations, so we have 2 separate samples. And what we want to do, it says the counts are clearly much higher in the summer. Give a 90% confidence interval to estimate how much higher the mean count is during the summer. Use degrees of freedom equal to the smaller of n sub 1 minus 1 and n sub 2 minus 1. Well, in this case, both sample sizes are 4, so both degrees of freedom are 3. So we're going to be using 3 for our degrees of freedom. Okay, to get this interval, the first thing we need to do is calculate x bar for each sample and s. So if I bring up my calculator, I think I've already put these in stat. Oh, got to turn it on. It shut off to save the battery. Okay, in list 1, I've put in the summer counts, and in list 2, I put in the winter counts. And then to find the statistics about those, I'm going to press stat, go to calc. I'm going to choose one variable stats. Now yours may come up with another screen. May ask you list 1. You can change list 1 pretty easy. In this one, it automatically defaults to list 1, but I could do second L1 to say find one variable statistics for the list of numbers in L1. So in this particular one, our first x bar sub 1 is going to be 2,131. And the standard deviation, make sure you use the S, so 902.88. And then n sub 1 was 4, so the degrees of freedom for 1 is 3. Now when I want to find the statistics for the second one, I'm going to go back to edit. I'm going to do calc. I still want to do one variable statistics, but this time I'm going to choose second list 2. And the x bar sub 2 is going to be 209.75. The S standard deviation for the second group is 138.26. N sub 2 is 4, so degrees of freedom 2 is 3. Okay, so the next thing I need to do after I've written those items down is to find my T, my critical T for writing my confidence interval. So to find that, I need to know the degrees of freedom, which is 3. We've already talked about that. And we want a 90-degree confidence interval. So when I go to my table, there it is. I'm back in table C. The degrees of freedom are in the left column, so I'm going to go to row 3, and it's a 90% confidence interval, so I'm going to come over here, and I'll be using a T, critical T of 2.353. Okay, there's the information I've written down here. So T asterisk 2.353. All right, confidence intervals, we're going to find the difference of the x bars here. Now, I automatically, because it said in the summer how much greater it was in the winter, so I took x bar sub 1 minus x bar sub 2, but I see in this one, I think if you enter them in the reverse order over here, you'll be fine too. But because they have negative values, I'm going to put them in so that mine matches there. So 209.75 minus the other mean. And then it's plus or minus our critical T, 2.353, times the standard error of the mean. And if you forget this formula, you can refer to the confidence interval was in the lower part of the left-hand column, right over there. This is the two-sample confidence interval that I'm looking at. So I need to do the square root, and this use my standard error of the mean here. So S sub 1, 902.88 squared divided by 4 plus 138.26 squared divided by 4. So when we put that in our calculator, let's see if I can get a calculator up here at the same time. And I'm going to start off by finding the difference in the two, 209.75 minus 2131 minus, to get the lower, 2.353 times the square root of 902.88 squared divided by 4 plus 138.26 squared divided by 4, close my parenthesis. That looks right. And we get negative 2995.87. We're a little bit off from theirs, a little bit lower. Not a whole lot, mostly due to the fact that they probably use more decimal places because they're using a software package. Don't worry about that. And then I just press second enter, which brings that whole long complicated thing up, because all I really need to do, where it said plus minus, change that minus to a plus to get the upper bound. And there's our negative 846.629 da-da-da. And again, just a few decimals off from theirs, again just because of rounding and software. So there you have it. That's our two-sample t-test, confidence interval, and an f-test thrown in just for fun. Well, I hope that works for you. Hope you guys have a great weekend. Let me know this weekend. I'll be reading my email off and on if you need some help, and I'll get that quiz opened up for you to take sometime this weekend. Talk to you later. Bye.